Okay, the first thing which we are going to study today is one parameterization of the curve, which is especially important. It goes for natural parameter. We will see why this natural parameter is important, at least in theory. So the natural parameter, I will use slides and explain slides. So you already know from last time, we have our curve. Let's say it's something like that. And then at point t is equal to a, so this is t is equal to a. We are in this point, and then we'll travel in this direction. And for example, at time capital T, we are here. And we know how to compute the arc length. So as the arc length when we travel from t is equal to a to t is equal to capital T, this is nothing else than integral from a to capital T of the norm of the derivative of f. This is what we did last time as the last thing. And now this function s of t, so this is the arc length function. And if we draw its graph, we get something like that. So let's say that here we have t, here we have s of t. At t is equal to a, let's say that we start, that we are interested only on this part when t is for, at least a. So when t is at least a, s of a is 0. So s of a is 0 because we started in a and then ended in a. So it's 0. And then when small t, when time is capital T, it's s of t. And then it grows because the arc length is positive, so it grows. It's a increasing function. So it's something like that. And you know from analysis that when we have an injective monotone function, then we can take, then we can compute its inverse. So since S is monotone, is strictly monotone, we can compute its inverse. Inverse S minus 1. And this will be defined on this interval here. So here we can compute its inverse. This will be domain of S inverse. And for example, if you take this point in the domain, what will be the value of the inverse? It will be this point here. So if we take here S naught, then S inverse of S naught will be this point, would be the corresponding T. And the same for the other points. So let's say that we take here one point. And what will be the value of the inverse at this point? It will be just the corresponding T. So inverse, in fact, maps from 0 to S of capital T. So this interval, this orange interval, back into the interval 0 at. So this orange interval is mapped into this interval here. So what is this inverse S inverse? It's nothing else than the function t of s. So we can write for this S inverse, we write this as a function t of s, because at the specific value of s, we get the corresponding time. So we can write this S inverse like the function t of s. So it maps 0 to s of t into the time interval at. And what we get, so we started with the parameterization of our curve. The parameterization was f of t. So this was parameterization of our curve from some interval into R2. So the parameter was t goes to f of t. But now we expressed but now we have this t of s, and we can define a function g, which now maps from the interval. So this initial interval was in fact a to capital T. But now we define a new function g, which maps from 0 to s of t, again into R2. And the rule is g of s is f of t of s. So g is just a composite f composite t, where we have to understand this t as the inverse of this function s, of this arc-length parameterization. So we are still on the same, this g, we are still, the trace of g is still the same as the trace of f, only that the parameter changes. So now our parameter is the arc length. Before it was some t, some time, for example. And it really maps into the proper codomain, because t of s, so we start with s, which is on the interval between 0 and st. And then t of s maps this s into the interval at. And then we apply f to these values, and we finish on our curve. So this is indeed another parameterization. This is another parameterization of our curve, where the parameter is the arc length. So the content of this slide was to introduce this arc length parameterization. Was this clear, or are there some questions? Okay, if not, then let's proceed. So why is this arc length parameterization important? Will be clear on the next slide. So it turns out that if our curve, so we start with our curve C, it's parameterized with some parameter t. And so C given by some parameterization from the interval I into R2. So the velocity vector is then f prime of t is the velocity vector, is the tangent or the velocity vector. And the length of this tangent vector depends on the parameterization f. But now our goal is that when we will compare different, when we will try to define the curvature of our motion, it will be important that our tangent vectors are of the unit length or are of the same length. So we would like to make this tangent vector of the same length independent of this parameter t. So we would like that all tangent vectors f prime of t for every t is of the same length. So that would mean that we are traveling along the curve with constant speed. And of course, if we just start with any parameterization, it doesn't mean that all the tangent vectors will be of the same length, meaning that the speed of the travel is the same. So we have to work a little bit to find a parameterization which would fulfill this condition. And we in fact already know such a parameterization. This is the natural parameterization. So the parameterization which solves this question, solves this problem, is the natural parameterization. So the parameterization with respect to the natural parameter, which we just studied. So we start with our parameterization f, then we calculate the arc length, so the natural parameter, and then the parameterized our curve C by this natural parameter S. And the proposition is, the proposition here on slide is states exactly what I wrote here. So if you have a curve C parameterized with natural parameter S, then the length of G prime S, or the length of the tangent vector in every point, is 1. And this is also the reason why this parameterization is called the unit speed parameterization. So we travel along the curve with the constant speed 1. And it's just a matter of some calculation. So let's go over those steps so that you will see that it's really nothing deep here. So we have this G prime of S. We compute this G prime of S. This is, in other words, it's dg over ds. So here in the third, in the second line, what we do is, in the second equality, what we do is just to plug in the definition of G. So G is F composite with T. So it's just definition. And now you know from analysis how to compute the derivative of the composite function. So we have to take the derivative of the outer function with respect to the corresponding parameter, and then multiply by the derivative of the inner function corresponding to the with respect to the parameter variable. So here we use the chain rule. It's called chain rule. So here we have derivative of f with respect to t in the point Ts times derivative of t with respect to s in the point S. So we have to compute this derivative dt over ds. And now if you go up where we defined S, so I would like to ask you if you remember from analysis what would be derivative of S in capital T. Do you remember from analysis how to compute if we are given a function with a definite integral, and then we take the derivative? So here we take the derivative. I will write in long notation. Here we take the derivative with respect to t, which is one of the limits of integration. So how do we compute what's the derivative of this function with respect to the parameter which acts as a limit of integration? Does anybody remembers? It's a very important theorem in calculus. So it's the so-called fundamental theorem of calculus, which is the basic connection between indefinite integral. So does anybody remember? Maybe if I write in the other way, so fundamental theorem of calculus. So maybe we will figure it out from this notation. Capital F of t, or let's say capital F of x, is integral from a to x of the function small f of t dt. So, and then we take derivative of f with respect to x and plug in some point x naught. Do you remember what was the result? So here the integration, the differentiation variable is just this upper limit of integration, and the result is then just plugging this point in the integrand. So it's f of x naught. So applying this fundamental theorem of calculus in our situation, so we have this, we take derivative with respect to this small t, which is the also the limit of integration. So what we do is just plug in the point where we evaluate the derivative. We plug this point into the integrand. So what we get is norm of f derivative in the point t. Okay, so ds over dt in the point t is norm of f prime of t. But if you look down, here we need to determine dt over ds. So now we justified this fact that s prime of t is norm of f prime of t. But we would like the other way, so t prime with respect to s. And this is again one theorem of calculus that if we have derivative which is non-zero, then the derivative of the inverse function in this point is just 1 over the derivative of the initial function. So if f, let's say some function such that f inverse exists, and f derivative of t naught, let's say, is non-zero, then f inverse derivative in the point f of t naught is just 1 over the derivative of f in t naught. This is also a theorem in calculus. And we use this here. So we know what's s derivative of t, then t derivative of s is just 1 over the derivative of s with respect to t. And now we plug this into the formula here. And what we get, so on the right hand side, we get f prime of t of s times 1 over norm of f prime of t of s. So what we get is this. So g prime of s, this is some velocity vector, this is some tangent vector, which points into the direction of f prime of t of s. So this is obvious because every parameterization, if the velocity vector is non-zero, then it should point into the direction of the tangent vector, which is unique. So of course it should point out into the direction of f prime, but it's of length 1 because we divided it with the norm of f prime. So if we take a length of norm of this g prime of s, we get norm of f prime over norm of f prime, which is 1. So we really prove that the natural parameterization is the unit speed parameterization. And everything what we needed was here the chain rule, and then fundamental theorem of calculus, and another theorem of calculus which connects the derivative of the function and the derivative of the inverse function. Okay, and let's look at one example. So this will be also important later when we define curvature. Especially this example will be important. So we have the circle, and we have the standard parameterization of the circle. This is so the circle with radius a. So let's say this is a. So we have the radius a. And this is its standard parameterization, you already know. So a times cosine t and a times sine t. And here t runs from 0 to 2 pi. It turns out very quickly that if a is not 1, then since norm of f prime of t, if you calculate this norm of f prime of t, we get so square root of first coordinate squared plus the second coordinate squared. So we get a squared in the parentheses cosine squared plus sine squared. So we know that cosine squared plus sine squared is 1. So what remains is then square root of a squared. And since a is positive, the result is a. And if a is non-zero, of course, then this velocity vector is not, the norm of the velocity vector is not 1. And this means that this parameterization f of t is not the natural parameterization, because the norm, the length of the tangent vector is not 0 in every point. But we would like to compute the natural parameterization of the circle. So we just use, so we just need to determine this arc length S. So S of t is then, so we start here in the point for t is 0. We have this point, we have point 1, a 0. And then we finish, let's say, at some other value of t, let's say capital T. And we compute this length. So this arc length is integral from 0 to capital T of the norm of f derivative t dt. We already know from this calculation here that f derivative t, norm of f derivative t is a. So this is integral from 0 to capital T of a dt. And this is, so we integrate constant function, so it's just a times capital T, because the integral of the constant function is t, and then we plug in the upper and the lower limit, and what we get is this a times t. Which means that, so S of t is then a times t. So inverse of S, how do we get inverse? So we have, we again have to recall from calculus, if you have some function in which there is an independent variable x and the dependent variable y, how to express, how to compute the inverse function. We just swap x and y. So here we would swap s and t, and we would get that, so let's say y is a times x, then we swap x and y. So we have to express x from this expression, and we get y over a, which means that S inverse is then a over s. I mean s over a.
Quick question.
Yes.
The minus from the derivative of the cosine is cancelled by the square, right?
Yes, yes.
Yeah, I just got a bit confused since the operands are in the wrong order. If we just like
yeah. So we should have a cosine t, and then this should be this term, right? And minus is cancelled there, and this one is here, yeah. Okay, thank you for this remark. So yeah, here we have S inverse is S over A. So our parameterization is then G of S. This is F composite with T of S. And this T is this S over A. In S, so what we get is A times cosine of S over A, and then A times sine of S over A. So maybe here it would be more convenient to not plug in S over A because it's a little bit confusing now. So maybe it would be better to write this as in this form, f of t of S. But we know that t of S, this is just f of S over A. And then we come here. So I will put this in the parentheses. So it's better to go like that in this direction. So this is the natural parameterization of our circle. The speed is in every point is 1. Okay, is there maybe some question?
So for all of these, the condition is that S is strictly monotone.
Yes, it has to be strictly monotone, otherwise we cannot compute the inverse.
So we can't compute this for, let's say, cycloid if the interval is too big. Because
yeah, but in the cycloid, it is monotone, because in the cycloid case, if you look in the cycloid case, so the arc length is always, so the function f, the derivative of S is non-zero, so it's growing, right? The arc length is growing all the time.
Yes, we are calculating the arc length. Yes. Okay.
So the problem would be if for some t we would stick in the same point. So the problem would be if we would say f of t is this, and then for t from some interval, and then we would stop in some point for some time. For example, that we would be in this point for 10 minutes and then proceed. So in that case, we would have to throw out those 10 minutes where we stop.
So if the velocity at some point is 0, then we wouldn't be able to calculate.
If the velocity is 0, not exactly velocity, but f of t, the parameterization shouldn't be like that, that we stop. For example, the velocity can be instantly 0, instantaneously 0, but we shouldn't be in this, it shouldn't be 0 for the whole interval. So it could be 0 for only in the point, but that doesn't mean that we stick in this point for some time. It only means that in this instant it was 0. But the problem would be if we stopped in this point for 10 minutes, then for the whole interval the velocity would be 0. So the velocity could be 0, but not, but it shouldn't have the, so the set of 0 shouldn't have non-empty interior. So it could be discrete. The set of zeros of the derivative could be discrete. It shouldn't have intervals inside.
Okay, thank you.
Okay, then this is the right point to do a break. After the break, we start with the curvature. So we will define the curvature of our curves. So this is the notion which measures how far from traveling along the straight line our curve is. So this example with the circle will be very important for defining a curvature. That's why we did it. Okay, we continue in 15 minutes. So the next topic is curvature. So we would like to measure how, for what amount does the curve deviate from being a straight line. This slide. So we have a straight line motion. Let's say that this is straight line. This the curvature, we would like to proclaim that the curvature of this this curve is 0. So let's say, as we will shortly see, that the notation for the curvature is this kappa. So I will just use this notation. So kappa is 0. With like this curve is not curved at all. The curvature is 0. But then if the curve is slightly bent like that, then the curvature should grow. For example, should be 1. And if it's bent even more, then it should be even bigger, and so on. So how would we measure, how would we define a proper amount which would measure how bent our curve is? So one way to define the curvature is to, let's say, we travel along the curve, and of course we have to define the curvature. Here I wrote kappa without any reference to the parameter. Of course we have to say at which point we measure the curvature, because it's not necessarily the same along the whole curve. So here we should write kappa of t is 0 for every t. Here kappa of t is 1 for this specific t. And here kappa of t is 2 again for this specific t, because it varies along the curve, and so on. We have to define some amount which can measure the curvature, so this deviation from being a straight line at each point. So it should be some limiting process, some limit will be involved, some derivative. So how would we define the curvature? Let's say that we travel some curve, along some curve, and then at some point with our car, at some point we just lock our steering wheel, and the car will start to move with the same curvature. It will travel with the same curvature along some circle. So in fact, in this point, how would we define the curvature? So the curvature should be somehow connected with the circle we would travel. We travel if we start traveling with the same curvature. With the same curvature. Of course, everything must be in the parentheses because curvature is not yet defined. So here we were traveling along this path. The curvature has been changing because the direction and the amount of the bend changed along this curve. But then here at this point, we locked the steering wheel and we started to travel with a constant curvature. So we made some circle, and we would like to somehow connect this curvature with the circle. And one natural parameter would be the radius of this circle. So one of the natural parameters measuring the curvature of the circle would be its radius. And what would be the relationship? What would be the nature of the relationship between the curvature and the radius? So if radius is smaller, so if radius is small, then we had to bend a lot in every point. So, but if radius is big, then we didn't have to bend a lot in every point. So this is small r corresponds to big curvature, and then big, so large r, this should correspond to smaller curvature, small curvature. So this means that this curvature kappa should be inversely proportional to the radius. So this means that if radius grows, then kappa should fall, and if radius falls, then kappa should grow. So the smaller the radius, the bigger the curvature. So this is somehow one way of defining the curvature. So we would like to connect it somehow with the radius of the circle, which we would do if we start to travel with a constant curvature from some point on. And it will turn out that the way we will define the curvature will really lead to this connection. But here is the more formal way of defining the curvature. I will write a picture and then we will explain the equations behind. So again, I will write, I will draw some curve, and then at this point, we have some velocity vector. And let's say that this velocity vector is of size 1, of length 1. So velocity vector of at point t. And then if we travel along the line, then it will be the same in for every parameter. The velocity vector will always point in the same direction. However, we made some bend here, so the velocity vector changed. So this is the velocity vector in the point t2. Then we did another bend, and then velocity vector changed again. So one way of measuring what was the bend is to somehow capture these changes in the velocity vectors. So one way for capturing the bend in the point is to compute the rate of change of the velocity vector. And of course, these velocity vectors must be of the same size. And we usually take them to be of unit length. So the rate of change of the velocity vector, if we travel with speed 1. So this would be one way for capturing this band. And if we have our parameterization, let's say that let's say that f is our parameterization of our curve. Then the velocity vector or the tangent vector in the point t will be f prime of t. So this is the velocity vector. But to ensure that it will be of unit length, what we do is here to normalize it, f prime of t over norm of f prime of t. This is the unit velocity vector. And to shorten the notation, let's say that this is capital T of t. This is only to shorten the notation. We define this f prime over norm of f prime as t over t. And in this notation, this rate of change, so this rate of change of the velocity vector in this notation is then just d of capital T over dt. And this is our kappa. So this is kappa of t. So this is the definition of the curvature. And of course we have to, so what's this dt or dt? This is vector, but we have to take its norm because we are only interested in its norm. So not on noting the direction. So norm of this change. Because this dt or d capital T over dt will be a vector, derivative of a vector function. So this will be a vector, and we are interested in its norm. And this will capture what we said here. So what's the rate of change of the velocity vector if we travel with speed 1 over our curve? And it will be some amount of the deviation from traveling along the straight line. And now the natural parameter enters. So why is natural parameter here handy? So if t is a natural parameter, so then this t of t is then, so f prime of t over length of f prime of t. But for the natural parameter, we know that f prime of t is 1. So it is then just f prime of t. So here f prime of t is 1. So here we essentially use that t is a natural parameter. And then kappa of t is then the norm of the derivative, norm of the second derivative of t. So in the case t is a natural parameter, this curvature is especially easy to calculate. We don't need to, because for a general capital T, we have to take the derivative with respect to t, and it turns out that taking the derivative of this expression can be can be quite nasty and require quite a lot of computation. However, if t is a natural parameter, then it's easy. then we just calculate the second derivative of t and its norm and get the curvature. Okay, so here we defined somehow curvature somehow intuitively with respect to circles, with respect to the radius of the circle, which we would make if we lock the curvature at some point. So if we do the same bend from some point on, if we start doing the same bend. Here we define this this curvature formally by measuring the rate of change of the velocity of the unit velocity vector when we travel along the curve. And now we would like to see that those notions are in fact connected, that they are the same. So what we would like to see, goal, if our curve is a circle, then kappa of t defined formally on the right side is really 1 over the radius of this circle. So we would like to show that this formal definition coincides with our intuitive definition of curvature. And that's why we used, that's why the last hour we computed the natural parameter for the circle of radius a, because now we can easily compute the curvature of this circle, because we know the natural parameterization of the circle. And this will be the content of the next slide. So before we proceed, was this clear? Or is there any question regarding the definition of curvature or this intuitive meaning? Okay, then let's look at the next slide. So recall from the last hour, we had this circle parameterized as f. So we had f of t was a times cosine of t, a times sine of t. This was some parameterization, the first parameterization of the circle we would make. And then we derived the natural parameterization. It's here. So the natural parameter was s, and the connection between the natural parameter and our initial parameter is t is s over a. So this is the natural parameterization of the circle of radius a. To compute the curvature, we need the second derivative. So first we calculate the first derivative. It's this vector. So a is missing here. A times minus, no, a is not missing. It's okay, because we also, the derivative with respect to s is then a times minus sine of s over a. And then we have to also take the derivative inside the argument of cosine. So it's 1 over a. That's why a and 1 over a cancel. and the same for the second coordinate function. And then we take, again, we take the derivative of this first derivative and get the second derivative, which is this, this vector. And now the curvature is just the length of this vector. And it's 1 over a, because we have 1 over a. So square root, this is square root of the first coordinate. So it's 1 over a squared. And then cosine squared s over a, plus the second coordinate squared, which is 1 over a squared plus sinus squared s over a. And again, since this is 1, cosine squared plus sine squared is 1, what we get is 1 over a. Okay, and this is exactly what we wanted. So we the first intuitive definition of curvature was that a circle of radius a should have a curvature proportional to 1 over a. And our definition of curvature gives us that the curvature is exactly 1 over a. And you see, if we compute the limit when a goes to infinity, then the curvature goes to 0. So when a goes to infinity, then the circle is not bent at all, so it degenerates into the line. So circle with infinite radius is in fact a line, and yeah, the curvature is then 0. On the other point, when a goes to 0, so when the circle gets really small, then the curvature gets big, so it grows to infinity, because then if a is 0, then the circle is just a point, and the curvature of the point is infinity. Okay, so this really connects this formal definition of the curvature with the intuitive one. And we also saw why the natural parameter is important, at least in this theoretical means. Otherwise, if we would try to compute the curvature of the circle with respect to this parameterization with t, without t being a natural parameter, it would require much more calculations and many more possibilities to make a mistake. And in fact, this curvature is also important for the practical purposes. For example, when they design roads or railways or roller coaster loops, or for example, ski jump in Planica, they want that this curvature of the curve smoothly, so goes smoothly from being a line into some circle. For example, so practically when they construct some of those roads or railways, they want that the curvature smoothly, so at first it's a line, this curve is a line, and then it starts bending, and the idea is this bend is smooth, that the bend isn't like that, but it's smooth, and that the bend starts to grow slowly. And for example, one of the how to express that this should be smooth is by saying that the curvature of our curve should be, for example, linear in S. So it should be linearly dependent on the parameter S. So on our parameter S is arc length. And we would like that as S grows, so here S grows, as we move along our curve, that this bend should also grow slowly, not rapidly as on this orange curve. And one way of saying that this should grow smoothly and slowly is to say that it's linear in S, for example, linear in S. That means that it's some k times S, where k is a real number. So smooth, slow dependence on S. And in fact, this Ks is equal to Ks. This is then norm of f prime of S. This equation, so f is here unknown. We would like to model this function f. F is here unknown. And it turns out that it's not very hard to figure out from this condition what f is. So we won't go through this really slowly, but I will only show you on the slides, and you can then read slowly by yourself. So one example. So here curvature is 2s in every point. Okay, here I made mistake. So second derivative should be ks. So say curvature is 2s. This 2 is only for computational purposes, so that in the process of derivation we don't have denominators. So it is only to cancel the denominator, these two. Otherwise, also for other, for any k, the derivation would be the same. So the derivation is like that, we take that, so we know that f prime of S is 1, because S is a natural parameter of our curve. That's why f prime of S should be 1. And if we express this unknown f in the form x prime s, y prime s, we know that x prime and y prime, they must lie on some circle. So since x prime, y prime s, norm of this vector is 1, in fact, those points lie on a circle of radius 1. For example, this is x prime of s, y prime of s. But we know that how to express the circle. Circle is cosine t, sine t, which means that this is cosine of phi of s, and then sine of phi of s for some unknown phi. So this x prime, y prime, this point corresponds to some point on the circle. So it's then cosine of some parameter and sine of some parameter. And this parameter is unknown, but it's a function of the s. That's why we have this condition. So we already know now a little bit more about f. It's of this form. F prime of s is cosine phi of s, sine phi of s. And now we can plug this into our condition on the curvature here. So curvature, this is the second derivative, the length of the second derivative of s. Now we know the form of the first derivative of f. So the second derivative is then, so what's the second derivative then? It's then minus sine phi of s and then phi prime of s. And the same for the second coordinate, so it's cosine phi of s, phi prime of s. But then taking the length of this, phi second prime of s. We did this computation a few times today. So sine and cosine, in fact, disappear because we get sine squared plus cosine squared. So they disappear. And what remains is then only phi prime of s. And this phi prime of s, from our condition, we know that it should be then 2s. And what remains is then just to take, so we need to figure out what this phi is, and we just integrate and get, so integrate this equation, and what we get is that phi s is s squared, because we integrate both sides, and you get s squared. And that's also the reason why we took 2 here. If we didn't take 2 here, then we would get here some constant s squared over something. So what we figure out is that f derivative is then this. So first coordinate function is cosine s squared. And the second coordinate function is sinus s squared. And to figure out what f is, we only integrate again. So we integrate again, and we get x of s is integral of cosine of u squared du, and y is integral of sine u squared du. And analytically, we are done here. Why? Because those two integrals are integrals of non-elementary functions. I mean, they are non-elementary integrals. Yeah, the functions are elementary because cosine u squared, this is an elementary functions, but its indefinite integrals cannot be analytically computed. So from here on, numerical stuff enters in. So we have to, in fact, compute those integrals numerically. And they are important in applications. That's why they have special names. So they are called Fresnel integrals. Because they appear in applications, as I've said before, when designing railroads with linear curvature with respect to the arc length. So maybe to show you the curve. So those are those two integrals. And here they are computed numerically. So the green one is x, and the red one is y. So how are these graphs drawn? So for every s, some numerical methods of integration are used, and then x of s is then we get the point s x of s. Then for another s, again, numerical methods for numerical integration are used, and we get s x of s. So we do this for enough points, and we get this curve. And the same for y, and we get this curve. And then if we draw f of s, so f of s is then x of s, y of s, we get this curve clotoid, so-called clotoid. So as s grows, then this curve does these circles, and for negative s, it does the same. It's the same picture, only in the fourth quadrant. So designing a railroad would be like that. So when we come here, it gets already too, the curvature becomes too big, because when S grows, also the curvature grows, because it's our condition was that K of S is 2S. So when S is big, K of S gets really big. So as S grows, of course, curvature is bigger and bigger. The circles it does are smaller and smaller. That's why the applicative part is probably only up to some extent, for example, like that. From here on, it gets too bent for too much amount. Okay. This was the curvature and its applications.
Just some question.
Yeah.
Why exactly is derivative of f circle? I mean, how did we get this?
So if we have the arc length parameterization, in the arc length parameterization, curvature is then the length of the second derivative. So we don't know what f is, but we assume that we will compute the arc length parameterization. So that's why that S will be the natural parameter. So we are searching for the parameterization such that f of S derivative, length of the derivative will be 1. This is because S will be the natural parameter. This is the second proposition. I mean, the first proposition from today's hour. So it was on the second slide. If you have a natural parameterization of the curve, then the length of the velocity vector will be 1 at every point. So here we assume that we will have, that we are searching for the natural parameterization of our curve. And since the natural parameterization always exists, we can do this assumption.
Yes, but then we say that first derivative of f equals cosine of phi and sine of phi.
Yeah.
So how can we know that?
So f derivative of S, length of f derivative of S is 1, right? That means
Yes.
that f derivative of S lies on the unit circle. This f derivative of S is some vector on the unit circle. This is for some S. And then for some other S, it's another vector on the unit circle.
And then we just describe the circle with cosine and sine.
Yeah, with cosine and sine, and which vector exactly we are referring to is determined by this unknown function phi. This phi for every, so phi will tell us for every value of S, let's say S goes from 0 to t, for every value of S, it will tell us the angle. So this phi maps S into the corresponding angle. Let's say alpha. And this angle will determine the appropriate f prime.
Okay, thank you very much.
Thank you for the question. Okay, this was the curvature. And now the last, almost the last thing studying the curves is plotting parametric curves. So I've already mentioned that we will study how to plot the parametric curve without MATLAB, at least to figure out an approximate shape of our curve. So the first thing is, let's just repeat how to compute the tangent, because determining vertical and horizontal tangents will be one of the most important parts of plotting parametric curves. it's here. So we have a plane curve, as always today. Let's say something like that. And then we would like to compute the tangent at some point. If everything is nice, like here, then let's say that this point is xa, ya. This is this point. So for the parameter t is equal to a, we get f of a, which is xa, ya. And then this line L, this tangent line, will be, so it will go through this point xa, ya. So L will be, it will go through xa, ya. And then plus, then we have to take a derivative of f in the point A. Okay, since we have just a vector function, we don't have a matrix, I can write this with a derivative. And then capture how much we move from the point A. So here we take x of t minus x of a, and then yt minus y of a. This would be this tangent line with respect to t. But if we try to express it in the usual way, where y is, so this is parametrically. But if we would like to express it in the usual xy notation, xy notation, we would like to express it in this form. So y is kx plus n for appropriate k and n. And when we know one point on the tangent and its slope, it's more convenient to express it in this way. So y minus the point is equal to the slope times x minus xa. So that means that when we are in the point, of course, that means that point xa, ya really satisfies this equation. That's why xa, ya really lies on this curve on this line, and it only remains to determine its slope. But for the slope, we know that it's the rate of change of y or the rate of change of x. So it's just y prime in the point A over x prime in the point A. So then this is the expression for the tangent. And it's this is true if everything is normal. So if we don't have a vertical or horizontal tangent, because for the horizontal tangent, so because x prime of A shouldn't be 0. So if x prime of A is 0, then we cannot compute this slope. In that case, the tangent is vertical. For horizontal one, in fact, this expression would be also okay, because for horizontal one, y prime would be 0, and we would still be able to calculate this slope. This slope would be 0, and we would get that y is equal to ya. So it's for the vertical, this expression would still work. Only for the horizontal, we would have a problem. But this is the general expression of the curve, which is for the tangent, which is this second point. So here, x prime of A shouldn't be 0. So if y prime in this expression is 0, then the slope is 0. And what we get is if y prime of a is 0, then in fact slope is 0. And we get that y minus ya is 0. So this means that y is equal to ya. So this means that the tangent is horizontal. This would be in this situation. So here, this is our tangent. This is our tangent, so y is equal to ya. It's constant in horizontal. But for the vertical line, so but if you would like to determine, for example, the tangent of this form. So the tangent of this form is in fact x is equal to x is xa, if this is the point xa. But in this point, what's true for y? So I mean, what's true for x? So in this point, x instantaneously doesn't change. This means that x prime is 0 here. So x prime of a is 0 here. And here, y prime instantaneously doesn't change. So y prime of a is 0. So we have three cases. This is case 1, where everything is nice. So the tangent is not even not horizontal, not even vertical. Then this is case 2, where the tangent is horizontal. And this is case 3, when the tangent is vertical. So how do we determine the vertical tangents? We determine the vertical tangents by solving this equation, x prime. So this is the condition, x prime of a is equal to 0. So we have to figure out for which parameters a, x prime is equal to 0. The condition for determining vertical tangents. So if the tangent is vertical, then x should instantaneously not change. This means that x prime should be 0. And the same for the horizontal tangents. Instantaneously, y shouldn't change. That means that y prime should be 0. So the condition for determining horizontal tangents. So determining horizontal and vertical tangents will be two important steps in plotting parametric curve approximately. And this will be the content of the beginning of the next hour. So is there some question? Okay, otherwise we continue in 15 minutes, so 20 past 11. So the next topic is plotting parametric plane curves approximately. And first we look at the general strategy, how to tackle this problem. And then we will go over one example, but you will also practice drawing at lab session. So we will just write the results and then try to draw a picture of our curve. Okay, so here is a general strategy. So some points to some steps to do are those ones. So first, we would like to know what happens when t is on the boundary of our interval. So either if the interval is the whole real line, then we would like to figure out what happens when t goes to infinity or minus infinity. That's why we compute those limits. Limit of f of t when t goes to plus or minus infinity. So this will give us how the curve behaves here and here in the endpoints. Then one piece of information which can be very useful are intersections with coordinate axes. So this point and those points. So the intersections with coordinate axes are yt is 0 and xt is 0. So we have to determine parameters when one of the coordinate functions is 0. Then it's also useful to determine those tangents which are vertical or horizontal, because we know that when the tangents are vertical or horizontal, the shape, so either it goes for local extrema in the x direction or local extrema in the y direction. So for vertical tangents, it goes for local extrema in the y direction, while for for horizontal tangents goes for local extrema in the y direction, and for vertical tangents it goes for extrema in the x direction. So we would like to find points where the tangents are vertical, and we know that we have to check where the derivative of x or the derivative of y is equal to 0. And then it's also convenient to find self-intersections, points, parameters where f of t is equal to f of s. If we would like to know the image of the curve more thoroughly in some neighborhood of some specific point, then we do some further investigation of this point. So this is this point to look for other helpful features. And then when we have all those calculations, so we calculate all those steps. When we have all those calculations, we got some points, for example, here, 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 here. And based on, since this is, for example, minus infinity, then this is -1, this is 0, and then this is 1, and this is 2. For example, then we know that we are traveling somewhere in this direction. So we know that we have to connect points somehow like that with the growing t. We'll look this on one example. Okay, I will write the example, because if I just use slide, then the picture is already done. So let's write it before without slide. So f of t is equal to t squared minus 1. This is the first coordinate, and then the second is minus t cubed minus t squared plus t plus 1. And we would like to plot the curve. So we will go a little bit fast over this. We won't do explicit computations. We will only write what are the results, because you will also practice this on lab sessions. So let's compute f prime of t. It's 2t minus 3t squared minus 2t plus 1. And now let's follow the procedure from the slide above. So what we have to determine is first asymptotic behavior. So limit when t goes to infinity of f of t. So the first coordinate is t squared minus 1. it goes to, so when t goes to infinity, this is infinity. The other coordinate is also polynomial of degree of e odd degree. That's why when t goes to infinity, the term of the highest degree prevails, and it's minus infinity. So minus t cubed, so it's minus in infinity. On the other hand, when we compute limit of f of t when t goes to minus infinity, the first coordinate is still infinity because it's even the even degree polynomial, and the second one is odd degree polynomial, so it's minus minus infinity cubed, so it's infinity. So we know that this will be in which quadrant? It will be in the fourth quadrant, and this will be in the first quadrant. Okay, then the second step is to find the intersection with coordinate axes. So we would like to compute xt is 0 and yt is 0. So xt is 0, it turns out that this is plus t is equal to plus minus 1. So if t is 1, the point is, so the first coordinate is 0, and the second coordinate is, if we plug in into the second coordinate and we get minus, we also get 0, yeah. Let me check. Minus 1 is minus 2, plus 1, yeah, it's 0. And when we plug in, so this is t is 1, and when we plug in minus 1, we get p is still, so we get p2, 0, and the second coordinate is minus 1 is plus, and minus 1 is then 0, and minus 1, 1. Again, we get 0. So in both points, both the parameter t is plus minus 1, both times we get a coordinate, the origin of the coordinate system. And for yt is equal to 0, now we already know that t is plus minus 1 are the solutions. But is there another? So we have minus t cubed minus t squared plus t plus 1. We can write this as minus t squared and then t plus 1 plus t plus 1. And this is t plus 1 times 1 minus t squared. It is t plus 1 squared times 1 minus t. So minus 1 and plus 1 are in fact both solutions, are all solutions. There are no other solutions. So those 2 points are intersections with coordinate axes. And let's compute the tangent. So how the local behavior in this point, we would need to compute the tangent. So f prime of 1 is what? F prime of 1 is 2 and then minus 4. And here f prime of minus 1 is minus 2, and then in fact we get 0. So this means since y prime is 0, this means that it goes for horizontal tangent. While for parameter t is 1, it's not horizontal tangent, but it's so it's this form: y minus y1 is equal to this k, which is y prime of 1 over x prime of 1 times x minus x1. But y1 and x1 are 0 because we are in the origin. And what we get is then minus 2, because y prime over x prime is minus 4 over 2. This follows from here. So we get minus 2x. So y is minus 2x. This is the tangent in the point 0, 0 at parameter t is 1. Okay. Then we need self-intersections. So f of t is equal to f of s. And it turns out that the only intersection is, we already know one intersection, P1, P2, and it turns out that this is the only one. So t is 1 and s is minus 1, and we get 0, 0. Okay. Then we need vertical and horizontal tangents. So vertical tangents. This is where x prime is 0. Since f prime is 2t, x prime is 2t, then the only solution is t is equal to 0. So this means that t is 0, and the point f0 happens to be minus 1, 1. So we just plug in t is 0 in the expression for f of t. So this is the vertical tangent, and the vertical tangent is so y is equal to, so x is equal to minus 1. Because we know that the tangent is vertical in this point, and x is minus 1 in this point. So the vertical tangent is minus 1, and the parameter is 0. This will be also important. And then we need horizontal tangents. So y prime of t is equal to 0, which means that minus 3t squared minus 2t plus 1 must be 0. We already know from here that one of the solutions is t is minus 1. And the point which we get is, so we plug in into the expression of f, and the point which we get is, so y is 0, and x at minus 1 is also 0. Yeah, we know from above, because t is minus 1 gives us 0.00. It's in fact P2. But we also have another solution, and another solution of this quadratic equation is t is 1/3, and the point which we get is minus 8/9 and 32 or 27. So this is just a calculation. This is the value of f for parameter t is 1/3. Okay, we calculated all the information we need, and now let's try to draw our curve, approximate the image of our curve. So for t is minus infinity, we know that we are in the first quadrant. We don't know exactly where, but both coordinates are infinity. So we should, we don't know how exactly the curve, if the curve has some asymptote, but we know that we are somewhere here. So we will, for our purposes, it's enough to write here t is minus infinity. We'll start somewhere from infinity in both directions. On the other hand, for parameter which is infinity, we will end up in the fourth quarter. So x will be infinity, but y will be minus infinity. Again, we don't know exactly what is the asymptote. If it exists, it turns out that it doesn't, but for our purposes, it doesn't matter. So let's write t is minus infinity here. And then we have intersection P1. So this is 0, 0. This point 0, 0. We come here first at parameter t is minus 1. Yes, minus infinity in the bottom. Yeah, thank you. So here it should be t is plus infinity. So the point 0, 0, it's first reached when t is minus 1. And we computed that the tangent is horizontal. So when t is minus 1, the tangent will be horizontal. So we know that as t is minus 1, the curve will look something either like this or like this. We don't know exactly, but so that's why I will erase this. But keep in mind that it's one of those forms, either parabola with extreme local extremum in the 0, 0, or so local minimum or local maximum in 0, 0. So it's t is minus 1. Then on the other hand, we are here also in the point 0, 0 also for t is 1. But here the tangent is minus 2x. So if I draw here 1 and minus 1, minus 2, so minus 1, this is 1. So the tangent will have slope minus 2. So it will be something like that. So this will be the tangent. Again, we don't know on which side of the tangent our curve will lie. We'll see this later, but this is the tangent. Then we know also that this 0, 0 is the only intersection. What else do we know? Okay, we know that the vertical tangent is exactly the only vertical tangent. The only vertical tangent is at t is 0, and the point is minus 1, 1. So minus 1, 1. This is our point. I need some other color. So this is the point, and the tangent is like that. And this is the only, this means that this is the only local extremum in the x direction. So only here it could change, it could bend back from, we know, now we know, since we start on the right side of this tangent, and this is the only local extremum, we know here that it will look like that. It can't be on the right side, on the left side of this tangent, because otherwise we couldn't end up in the right side of the tangent again, because this is the only local extremum in the x direction. Then the horizontal tangents. So and right t is 0. Then the horizontal tangents are 2. One is this t corresponding to t is minus 1. We already have it. And the other is at t is 1/3. and the point is -8 over 9. -8 over 9. And 32 or 27, so it's somewhere here. In fact, it should be below this. Yeah, it's now my picture is too dense, so it should be below this orange, below this orange line. Otherwise, there should be another. Otherwise, our tangent should be on the other. Our curve should be on the other side of the tangent. So I will a little bit change this orange line a little bit. So I will write it a little bit more up. So now this is -8 over 9, and here 32 over 27. So this is this point corresponding to t is 1/3. Okay, maybe it would be good to draw another picture here, only with the points, without all those tangent lines. So we have this point, t is -1 and t is 1, and then we have t is 0, and then we have t is 1/3, and then we have 2 asymptotic points. This is plus infinity, and this is minus infinity. And we know that now we already know. So those 3 points, on one hand, this point 0, 0 is self-intersection. On the other hand, all those 3 points are local extrema. So t0 is local extremum in the x direction, while t is 1/3 and t is -1 and +1 is the vertical extremum. So knowing this, the only way for our curve to go through those points is to be of this shape. If the shape would be different, then there should be other local extrema. So we know that t0, the extremum must be, so the tangent, the curve must be on the right side of the tangent. On the other hand, we know that in the point t is 1/3, the curve should be below this vertical tangent, because if it was above, then we would need other extrema to reach points below. And we also know that this origin, the curve should be above the tangent in the origin. So this is the only way the curve could be in those 3 points. And then we just look, we started minus infinity. When t was minus infinity, we are in this point. And when t is -1, we are in the origin. And on the way from minus infinity to -1, there couldn't be any other local extrema. So our curve must be monotonic in this on the interval between minus infinity to -1. So the only way is that it looks like somehow like that. We don't know exactly the curvature, but it's monotonic. And the same is true for the interval between 1 and infinity. Since there are no other local extrema in the x and y direction, there are no other vertical or horizontal asymptotes, it should be, from t is 1 to infinity, it should be monotonic. And again, so it should be monotonic. There are 2 possibilities. It is either like that or like that. So the first would be convex and the other is concave. But if it's this type 1, then it should be like that here. And it will have another extremum in the x direction, which is not which doesn't happen. So in fact, it's not convex. It must be concave. So this type 2 is appropriate. So it will be like that, somehow like that. Again, we don't know exactly how shaped it is, how bent. And from 1/3 to 1, we should connect 1/3 to 1. And again, we don't know how exactly, but this is one possibility. And of course, it should be smooth. So it's in fact like something like that. So we can at least draw approximate picture of our curve. So if we would like a more proper picture, we would need to compute further local behavior. We would need to determine further local behavior of our curve in the specific points, but approximate picture is the one I've just drawn. Okay, and on the slides you can see the picture with drawn with Mathematica. And yeah, this is the proper picture with Mathematica. But even without Mathematica, we could, knowing only the information on the self-intersections, vertical, horizontal asymptotes, especially asymptotes are very important because we know then what are the local extrema in both directions. And yeah, all those information helped us to draw this sketch. Okay, and you will practice this on lab sessions. Okay, we almost finished with curves. Let's recall something about calculation of the area below the curve. So there are two questions regarding calculating the area below, so bounded by the curve. You've seen both of them at analysis. So the first is we have this parametric curve, f of t is x of t, y of t. This is the picture of this curve. And one question is, so there are two questions which we can ask to two areas which we can compute. So let's say that this is our curve. So the first possibility is that we are interested in the area below the curve, while the other possibility is that we are interested in the area bounded, so described by the position vector of our curve. So position vector here and here. So position vector then describes this area. So there are two questions. Either we would like to compute area below the curve or area bounded by the position vector of our curve. And we know how to compute both of them. So the first is just integral. So here we have to express this curve in this dependence y of x. So x here goes from a to b. Let's say that it goes from x of a to x of b, because xt and yt are now coordinate functions. So x goes from xa to xb, and y goes from, and then y, we must know how to express y in terms of x, because then this is the graph of the function y of x, and you know from analysis that the area below the graph of y is then integral of y x dx of from x of a to x of b. But if you want to express this in terms of the parameter t, we do the substitution. So we know that x is x of t, and then dx over dt is then x prime. And so dx is x prime dt. This is just the substitution of variables. This is known by substitution of variables in analysis. And so we plug this, we do the substitution of variables, and what we get is then integral of this function y of x of t times, here we have x prime of t dt. And then what are then the borders of integration? So yeah, then the borders of integration are from a to b, because x goes from x of a to x of b, and the lower limit for t is then a, the upper limit for t is b, so the borders change, so we have a and b. So yeah, and here on the slides we have absolute value of y to cover also the case where the curve goes below x-axis. So if it's above x-axis, then we don't need absolute value. Okay, and here is one example. If you would like to compute the area under one arc of the cycloid, so you can do this example by yourself. We have this cycloid, so you have to you would like to compute this area. You just plug in this. So you just plug in xt prime and yt into the formula, and a goes for a is 0 and b is 2 pi. So this was the first possibility. And now the second possibility, you probably remember from analysis that there was a formula for calculating also this curve. But let's now see why this formula, we will recall this formula and we will see why it's appropriate. So it's that one. So you see, again, we will derive this formula with Riemann sums. So I will write a picture again. We have this curve, and we would like to compute this area. And the idea is to, again, divide this arc on many, as when we were deriving the formula for the arc length, also for the area under this arc. What we do is here divide this arc into many points, And then we divide this area into triangles. And so we have here f of t naught, f of t1, f of t2, and so on. Those are position vectors in these points. And now let's recall how to compute the area of the triangle. If we have a triangle, let's say that this is vector A, this is vector B. So one way to calculate the area of the triangle is to compute the vector product of A, the cross product of A and B. So then we get the area of the length of this vector. The length of this vector is the area of the parallelogram with sides A and B. So we need only half of this area. So this is 1/2 of the length of the cross product of the sides of the triangle. And if f of t naught, okay, so this is the area of one triangle. And you see we have here the division of our arc on many pieces, and then we have many of those triangles. And now again, the idea is to do a linear approximation. We will approximate. So we have here f of t naught, and here we have f of t1. We will approximate f of t1 linearly with a tangent. We do a tangent, and then we approximate this triangle with this a little bit bigger triangle in this case. So f of t1 will be approximately f of t0, f of t naught plus derivative of f of t naught times t1 minus t naught. So this is the tangent in the point t naught. So we approximate f of t1 as if it would lie on the tangent. And why was this good? Because now f of t naught cross product with f of t1 is approximately f of t naught cross product with, and then we plug this f of t naught plus f prime of t naught times t1 minus t naught. So cross product is linear, so it's f of t naught cross product f of t naught plus f of t naught cross product f prime of t naught times t1 minus t naught. But the cross product of two vectors which are the same is 0, because then we get the degenerate parallelogram. So this is a 0 vector, so it cancels out. And what we get is this cross product times delta t naught. But f of t naught, I will shortly finish. Let me just finish the derivation of this formula. F of t naught is x of t naught, y of t naught, and then f prime of t naught is x prime of t naught, and then y prime of t naught. And now you can recall how to compute cross products. We get exactly, we get, let me just check not to do mistakes. So we get, so in fact, cross product of those two vectors, the third coordinate, we can regard the third coordinate as 0. It doesn't matter what's the third coordinate. the triangle, let's say that this triangle lives in the z is equals to 0, but it doesn't matter. So it's constant. The third coordinate is constant. So when we compute the cross product of those two vectors, we get 0, 0, and the third coordinate is x, y prime minus y, x prime. Of course, everything computed in T naught. Okay. And so what is then our area? So this is then the approximation for the, so 1/2 of this, of the norm of this vector. So 1/2 of this third coordinate is then the approximation for the area of one triangle. And as always in analysis, what we do is to do the limit. We do the limit division, a lot of points. Those T1 minus T0 go to, so those differences between the consecutive T's goes to 0. And what we get is, in fact, the Riemann sum. So the area is sum of length of, so 1/2 of f t I cross product f t I prime times delta of ti when e goes from 1 to n. And this is by what we just computed, e1 to n, 1/2 of absolute value of x, y prime minus y, x prime in ti times delta ti. So this is, here we used, in this equality, we used what we've just computed. And then, and now we this is in fact the Riemann sum of some of this function. So we do a limit with those delta t's go to 0, and what we get is the integral of the function 1/2 of x y prime minus y x prime dt when t goes from a to b. So from the left endpoint to the right endpoint. And probably you recall this formula for analysis. So this is area, which we wanted, area of the position vector. Okay, this is everything for today. Next time we'll study surfaces, parameterization of surfaces, and then we can start with our last model. So the third model of this course, which is dynamical models. Are there maybe some questions for the end?
Yes, I've got a question regarding homework.
Mm-hmm.
About QR decomposition.
Mm-hmm.
For example, in Octave, I wrote